Good morning students. Today we are going to start our engineering mechanics practicals. In our engineering mechanics lab, all together we are going to conduct the 7 experiments. Here as per syllabus only 6 are mandatory here, but that 6 we are going to complete, but one more additional experiment we are going to conduct. So at least 7 experiments we are going to conduct in our engineering mechanics lab. So the first experiment which we are going to learn is the verification of law of Polygon of forces. Verification of law of Polygon of forces. Now before explaining this experiment, I would like to give you some basic information or basic knowledge about this law of Polygon of forces. Now all of you know about the vectors, scalars and vectors. A vector is a physical quantity which is having the magnitude as well as direction. For example, the force. The example of the vector quantity is force. Force is a vector quantity. For the complete specification of the force, we require its magnitude as well as direction. The next point is how we can add the vectors. You have studied the addition and subtraction of vectors. Now the next one is how to add the vectors. Now for addition of the vectors there are 2 methods. The one is the graphical method and other one is the analytical method. In analytical method we express the vector in terms of I, j, k, in terms of the unit vectors along x, in terms of the component along x, y and z direction, and we add that components. So that is the analytical method to add the vectors. The another method is the graphical method. We can use the graphical method to add the vector. Now which are the graphical method to add the vector? The first one is the triangle law. You must have studied the triangle law of vector addition. The second one is the parallelogram law. And third one is Polygon law. These are the 3 graphical methods with the help of which we can add the vectors. Now in graphical methods, to add the vector, the first important thing is to express the force graphically. How we can express the force graphically or any vector? It may be the acceleration vector, it may be the velocity vector. So how to express any vector graphically? So for example, suppose this is one force whose magnitude is 100 Newton, which is inclined at an angle of 30 degrees with horizontal. This is the direction, this is the magnitude. Now how to express this or how to represent this force graphically? To represent this force graphically, draw a line parallel to the line of action of this force. This line along which the force acts is known as its line of action. So to express or to represent this force graphically, draw the line parallel to the line of action of this force. Since we have drawn the line parallel to the line of action of the force, means this line is also inclined at about 30 degrees with horizontal. And then select suitable scale to represent the magnitude. So here I am representing the, I am selecting the scale. Suppose 1 centimeter is equal to suppose 20 Newton. If I select this scale to represent the magnitude, so to represent this 100 Newton force, I require the length of this line segment of 5 centimeter. 100 divided by 20, so 5 centimeter. So this 5 centimeter length AB represent a force of 100 Newton. So in short, to express the force in graphically, to represent the force graphically, you just draw the line parallel to the line of action of that force and select suitable scale to represent its magnitude. Here I have taken the example of force. Here in a similar way, you can represent velocity, acceleration, displacement in vector form. So this will be required for the graphical addition of the vectors in triangle law, parallelogram law and polygon law. Now what is the triangle law? For example, suppose the 2 forces are acting on a body. Here this is P and this is Q, which makes angle of theta degree with horizontal. If I want to add these two force vectors, okay, so triangle law states that when two forces act on a body are represented by the two sides of a triangle taken in order, then the third side of that triangle represents their addition taken in opposite order. I am talking only about the addition. Okay, so if suppose I want to add these two vectors here, which is P and Q, so you have to represent this force P graphically. So this length represents the force P graphically with some suitable scale. Then draw the line parallel to the line of action of this force Q here, and with the same scale you have to represent this force Q also. This length represent this AB length represent the force P, and this BC length represent the force Q by using the same scale. Okay, so when these two forces act on a body are represented by the two sides of a triangle taken in order, then this closing side or the third side of the triangle represents their summation. So this AC vector represents the force P plus Q. Okay, this is the summation. Okay, in parallelogram law also it is the same. Here parallelogram law and triangle law are applicable only for the two vectors. Or when we want to add the two vectors, here we can do the triangle law and the parallelogram law. Whereas when we want to add the more than two vectors, here we have to add the law of polygon. Okay, now what is the parallelogram law? In parallelogram law, if these two forces are, or these two vectors are acting on this body, are represented graphically by the two adjacent sides of a polygon. Sorry, parallelogram. Yeah. Here we have represent these two forces as the two sides of a triangle taken in order. Here in parallelogram law we are representing them as the two adjacent sides of a parallelogram. If I complete this parallelogram, here in parallelogram the opposite sides are equal and parallel, then this diagonal which is passing through the intersection of these two vectors represent their summation. So this is P bar plus Q bar. Okay, if you measure this length of the diagonal, which gives you the summation of these two vectors. Here, this length gives you the magnitude, and if you measure this angle, this gives you the direction. Let denoted as alpha. Okay, so this is the triangle and the parallelogram law, which is applicable to add the two vectors. It may be the force vector, it may be the velocity vector, or any other vectors. Okay, now the third one is the polygon law, which we have to study here. Okay, when more than two vectors are there, we have to use the polygon law. Yeah, and the polygon law is just extension to the triangle law. It is similar to the triangle law. Okay, here two forces are there, that's why we got the triangle. But when more than two vectors are there, and if you follow the same procedure, here that figure will be the polygon. It may be any polygon. Okay, it will be the quadrilateral, it will be the pentagon, depending on the number of vectors which you are adding. Okay. Now what is this polygon law? In polygon law, suppose there are a number of vectors. Suppose this is P, this is Q, and yet this is S. These are the three vectors. Here we know their magnitude as well as direction, and we have to add these three vectors graphically. Okay. So for that we have to use the polygon law. Now what polygon law states? Polygon law states that when number of vectors are there, okay, and to add them, you have to represent these forces graphically as a side of a polygon taken in order. Okay, so I am going to represent these forces as the sides of a polygon. Let this force, this line AB represent the force P with some suitable scale. You have to decide the scale. Here you have to decide the scale such that this figure, while deciding the scale, you have to just observe the force or vector of minimum magnitude and maximum magnitude, and according to that you have to decide the scale such that this figure should not be very small or very big. Okay, so represent these vectors as the sides of a polygon taken in order. So this AB line represents the force P. Now from this head end, you have to represent the next force here, which is Q. So draw the line parallel to the line of action of this force Q. This line, such as BC line, represent the force Q. If this angle is theta, this will also be theta because these two lines are parallel. Then from this head end, represent the third force here, third vector, which is S. So this CD line represents the vector S. Here I have drawn the line parallel to this. if suppose this angle is theta 1 with positive x axis, here, then this angle will be theta 1 with positive x axis. Okay, so when number of vectors are there, and if you want to add them, you have to represent them, these vectors graphically as the sides of a polygon taken in order. You will observe that all the vectors are in order. You can use any vector. After P, need not necessarily that you have to go for Q. You can go for S also. You can select any sequence. Yeah, but all these should be in order. Order means the next vector you have to start from the head end. Yeah, this vector you have to start from the head end. Okay. So if I represent these vectors as a side of a polygon, then this closing side of the polygon represents their summation. Okay. So this line AD represents the vector P bar plus Q bar plus S bar. This gives you the summation. Closing side represents the summation of that vector. Here in triangularity also it is similar, but in triangle only two forces are there. That's why this figure we got as a triangle. When more than two forces are there, this is the polygon, and it is known as the law of polygon. Here, basically, these are the laws which are used to add the vectors. Related to our subject of engineering mechanics, in which we are going to deal with the force systems. Okay, we are going to apply this law of polygon to the force systems, and that's why it is the law of polygon of forces. Okay, related to our subject, we are using it as a law of polygon of forces because we are applying this law of polygon to the force systems. Otherwise, you can apply it for the vector summation, for any vector summation. You can add acceleration vector, velocity vector, displacement vector, or any other vectors also. Okay, we are going to use it for the forces. Okay, so just remember what is the law of polygon of forces then. Here suppose on any body, number of forces are acting, like it is F1, F2 and F3. Okay, and if I represent these three forces by the three sides of a polygon taken in order, then this closing side represents their summation. Understood? This is the basic concept of the law of polygon of forces. Here, now we have to verify the law of polygon of forces. Here, before proceeding for this verification of law of polygon of forces, this was the basic concept which you have studied up to in your 11th and 12th standard exam. Okay. Now, since in our subject we have to study the different type of force systems, here force and force system. Here I assume that you people know what is in the force and how can you define the force, what is the unit of the force, and other things related to the force. Okay. So I am not going in deep about the force. Here only I would like to tell you about the resultant. What is meant by resultant of a force system? What is meant by resultant? Okay. Now, what is the resultant? Consider this is one body on which suppose these two forces are acting. F1, F2, let angle between them is theta. Okay. So, resultant of this force system defined as a single equivalent force. What is resultant? Resultant is a single equivalent force of the given force system which produce the same effect as this number of forces producing on the body. Okay. There are two forces F1 and F2. Whatever will the effect produced by these two forces on the body, if the same effect if we created by using a single force here, then that single force is known as their resultant. Okay, in the combined effect of these two forces F1 and F2 on the body and the effect of this single force on the body, if this effect is same, we can say that this single force is the resultant of these two. Okay, so resultant is a single equivalent force which produces the same effect as the number of forces producing on the body. Okay, then which are the different methods to find out the resultant? Which are the different methods to find out a single equivalent force? Okay, now again to find out the resultant, there are two methods. One is the analytical method, other one is the graphical method. Before explaining this analytical and graphical method to find out the resultant, let me tell you, I explain you the definition that it is a single equivalent force for these two. Now, since it is a single equivalent force for these two, this resultant force is nothing but the vector summation of these forces. If I take the vector summation of these forces, I will get the resultant force. Okay, here resultant is a single equivalent force, but how we can find out? Here by adding the forces vectorially. Okay, force is a vector quantity, we can't take directly. Suppose this F1 is 20 Newton and F2 is 30 Newton, so resultant won't be equal to 50, 30 plus 20, because it is a vector quantity. We can't add them like a scalar. Okay, so we have to take the vector summation. Yeah, so to find out the resultant, we have to take the vector summation of the forces. And how we can take the vector summation? Again, there are two methods. One is the analytical method and another one is the graphical method. Again, in graphical method, same method we are going to use the triangle law. Here, second one is parallelogram law, and third one is the polygon law. Since all these three are the graphical methods to add the vectors, and we are going to use these three graphical methods to add the forces to get the resultant, we can say that related to our subject, we can say that these are the graphical methods to find out the resultant. Okay, triangle law, parallelogram law, and the polygon law are the graphical methods to find out the resultant. Okay, so this is all about the resultant. It is just a vector summation of all the forces. Now to find out the resultant in analytical method, listen to me. In analytical method, we are going to use the resolution method. We are going to resolve the forces and we are going to find out the resultant. And in graphical method, we are going to use the triangle law, parallelogram law, and the polygon law. Out of that, here we have to study the law of polygon of forces. We have to verify the law of polygon of forces. Okay, here by doing some experimentation, we have to verify that law. Okay, so to verify the law, basically every student should know what is the law of polygon of forces. Okay, now before coming to that law of polygon that already I explained, we are since we are verifying it by using the analytical method as well as graphical method. Yeah, so what is this resolution method? Okay, I already told that the resultant is a vector summation of these two. Let's consider these two forces. Yeah, it is a vector summation of these two forces. Yeah, but we cannot find out this resultant directly R equal to F1 and F2. We cannot take the scalar product. Scalar product summation. Okay, to find out the resultant, we have to take the vector summation. And in vector summation, we cannot add the magnitude directly. Okay, then what is the method? Either you have to express these forces in vector form and you have to add them. Here express each force in terms of I, J, K and add them. Here and this coefficient of I, coefficient of J and coefficient of K are nothing but the component of that particular force along X, Y and Z direction respectively. Okay. Then instead of expressing them in the vector form in terms of I, J, K, in resolution we are going to do the same thing but in a different way. Okay. What we are going to do? Here we resolve each force into two rectangular components along X and Y axis. Yeah, suppose this force is F2 and suppose this angle is instead of this, if I consider this as a theta1, here then resolve, it is actually in the second quadrant, so its X component will be towards left and Y component will be upward. If this angle is theta1, then this component will be F2 cos theta1 and this component will be F2 sin theta1, provided this angle is theta1. Okay, the component adjacent to the given angle is cos component. Okay, here we have to resolve this force into two components such that the combined effect of these two components should be equal to this original force F2. Okay, this F1 is along the x-axis itself, so its x component that force itself and y component will be 0. In this way, I have resolved this force system. Similarly, if I resolve this resultant, here its x component is Rx and y component is Ry. Okay, here. When we study this lesson here at a time, here in details we will study about this resolution process. So I have resolved this resultant in two components. Now I already told that the resultant is an equivalent force for this F1 and F2. Here I cannot find out the magnitude of the resultant directly by adding the magnitude of the component. Here because they are acting in a different direction. Here, but I can calculate this Rx by taking the algebraic summation by adding this F1 and F component along x-axis directly by using the suitable sign convention. because they are also the vector quantity. These components are also the vector quantity, so we cannot add them directly with their magnitude. We have to consider their direction also. Yeah. But since this Rx in x direction, this f1 and this f2 cos theta 1 are also in x direction, so by taking some suitable sign convention, we can add them directly instead of expressing them in the vector form. Okay. So we can write this Rx equal to f1 and assume that force towards right positive. So this f1 is positive minus, why minus? Because it is acting towards left. So it is minus f2 cos theta 1. In this way I can calculate this Rx and Ry equal to, here this is the vertical component of the resultant, which is equal to the summation of the vertical component of these forces. Y component of this f1 is 0 and y component of this f2 is upward, that's why it is positive. Here we are considering that for adding the forces along x direction, we are using the component towards right positive. Adding the forces along y direction, we consider the upward force positive. So if I consider upward force positive or upward component positive, then the y component or vertical component of this f1 is 0 and vertical component of this f2 is upward, that's why it is plus f2 sin theta 1. In this way we can get Rx and Ry. Once you get this Rx and Ry, here we can use the triangle law to calculate this R, or by using the triangle law directly we can write down the mathematical expression, this R equal to under root of this Rx square plus Ry square. And this Rx is nothing but the summation of all x component. This is the summation of all x component. We can write it as the summation of fx. And this Ry is nothing but the summation of all y component, which can be denoted as the summation of fy. Sigma stands for the summation. This is the summation of all components acting along x direction. This is the summation of all forces acting along y direction. Here, so this resultant can be written as under root of summation of fx square plus summation of fy square. This is the magnitude of the resultant and direction of the resultant. Here this resultant makes an angle of alpha degree with horizontal. Here, so we can find out this alpha equal to tan inverse. It is Ry upon Rx. Or we can write down this alpha equal to tan inverse summation of fy upon summation of fx. In this way we can calculate the magnitude and direction of the resultant analytically. This is the analytical method, which is the resolution method. We have resolved the forces and we have taken the summation of all x component, which gives you the Rx or summation of fx. We have added all the y component, which gives you the summation of fy, which is equal to the Ry, and with help of this fx and fy we have calculated the resultant by using the triangle law. This is the triangle law. Okay, if I represent this summation of fx along x axis, summation of fy along y axis, then this closing side represent their resultant. And here we can use the Pythagoras, so R equal to under root of summation of fx square plus summation of fy square. This is nothing but a triangle. Okay, so this is the resolution method, where then of which we can calculate the magnitude as well as direction of the resultant. Okay, now when we find the resultant of any particular force system, here I have already told you that this is a single equivalent force for the given force system, which produces the same effect. And single equivalent force is always an unbalanced force. Whenever any single force acts on body, it is always an unbalanced force. Here, if I consider this body, if I resting on this surface, here it is in the complete state of rest under the action of two forces. Which are the two forces here? One is the weight, other one is the normal reaction. But if I apply one unbalanced force in the horizontal direction, because of which it starts moving in the direction of that unbalanced force with some acceleration. So remember, whenever any unbalanced force acts on a body, that unbalanced force is always responsible to produce certain motion. Okay, it is always an unbalanced force which produces the motion. Okay, then the next term which I would like to tell you is the equilibrium. You must have learned something about the equilibrium. Okay, now in short I am going to explain. Now what is equilibrium? When a balanced force system is acting on a body, we can say that it is in equilibrium. When a balanced force system acting on a body, we can say that it is in equilibrium. What I am saying? Balanced force system. Equilibrium is nothing but a balanced force system. Okay. And when a balanced force system acts on a body, there are two different effects on the balanced force system. One is Because of the balanced force system, the body may remains in the state of rest, or it may remain in the state of uniform motion, uniform linear motion, not uniform angular motion. Okay, when a body is moving with a uniform linear motion, it means that during the motion, if its velocity is remain constant, uniform, we can say that it is moving under the action of balanced force system. If it is moving, if under the action of certain force system, if the body is moving with a uniform linear velocity, we can say that it is in equilibrium. Okay, so equilibrium doesn't mean that only state of rest. Even if the body is moving with a uniform linear velocity, we can say that it is in equilibrium. So equilibrium is nothing but a balanced force system. Now, when any body is moving with a uniform linear motion, is when velocity equal to constant, acceleration equal to 0. And according to the Newton's second law, here summation of F equal to ma. If a equal to 0, this term becomes 0, means the algebraic summation of all force vector is equal to 0. If algebraic summation of all force vector is equal to 0, it means that it is a balanced force system, or we can say that it is in equilibrium. Okay, so when a body is in equilibrium, it means that the force system is in the state of rest, or it is in the uniform linear motion. Okay, and when a balanced force system is there, or when any force system is in equilibrium, here there is no any unbalanced force. Yeah, and since there is no any unbalanced force, so for that particular force system, the resultant force is equal to 0. Okay, so for any particular force system, if the resultant force is 0, for concurrent force system I am talking. Okay, when a resultant force is equal to 0, we can say that it is in equilibrium. I am talking only about the concurrent force system. Okay, here for a complete equilibrium, there should not be any translational motion, there should not be any rotational motion. Here for rotational motion, the torque or the moment is responsible. Okay, here, so it is not always true कि अगर unbalanced force 0 है, it doesn't mean that always it is in equilibrium. Here, if the unbalanced force is 0, there may be an unbalanced moment of torque present in the system, and that unbalanced moment of the torque may produce the rotational motion. Okay, so just we are talking about the concurrent force system. So remember about the concurrent force system, it is in equilibrium. Here its resultant force is 0, or we can say that vice versa. When the resultant is 0, the force system is in equilibrium, or if it is in equilibrium, the resultant force is equal to 0. Okay, yeah. So this is all about the basic things which are required for the law of polygonal forces. Yeah. Now in law of polygonal forces, we are going to, here we have to verify the law of polygonal forces. Okay, in law of polygonal forces, what we are doing in our laboratory, we are creating one concurrent force system. Concurrent force system. Concurrent force system means when the line of action of all forces are acting at one point, then it is known as a concurrent force system. So in our laboratory, they are going to produce such type of force system, which consists of 5 forces. Okay, such type of force system we are going to create. Yeah, and for this force system, we are adjusting the magnitude of all these 5 forces and their angles, yeah, or in their direction, such that this force system should be in the complete equilibrium. The force system should be in complete equilibrium. Here we are going to arrange these forces and their angle, their magnitude and angle such that here the force system should be in the state of rest. Means it is in equilibrium. And if it is in equilibrium, just I told that if it is in equilibrium, it is in the state of rest. And if I ask you for this concurrent force system which is in the state of rest, what will be the resultant? So resultant has to be equal to 0. Okay. Now, if this is a concurrent force system which is in equilibrium, yeah. Now with this concurrent force system, if I draw the polygon, yeah. So I am representing all the 5 forces. Here to draw the line to represent these 5 forces graphically. Draw the line parallel to the line of action of the first force. Then draw the line parallel to the line of action of the second force. Then draw the line parallel to the line of action of the third force. Draw the line parallel to the line of action of the fourth force, and draw the line parallel to the line of action of the fifth force. Okay. Now, if suppose this, if when you represent this fourth force and the fourth force in at this point, suppose this is A, B, C, D, E, and suppose this is A dash. If the fourth force in at this A dash here, then this closing side of the polygon represent the resultant of these five forces taken in opposite order, because resultant is nothing but a vector summation of all the forces. Okay, so this closing side represent their resultant. Okay, and I told you that if the resultant is present, means the force system is unbalanced force system. Here, if the resultant present है तो it can't remain in equilibrium. It will be in the motion. Okay, but this force system is in equilibrium. We have arranged it like that. It should be in equilibrium. And if it is in equilibrium, here then this resultant has to be equal to 0. And to get this resultant 0, this last point must coincide with the first one. Okay, it means that for the system to be in equilibrium, here the force polygon must be a closed figure. You can say that this is a graphical condition of equilibrium. There are some analytical conditions also. Okay, so what is the graphical condition of equilibrium? If a certain force system is in equilibrium, and with that force system, if you draw the force polygon, it must be a closed figure. This last point must coincide with the first point. Here, if the resultant is 0, then only we can say that it is in equilibrium. Otherwise, it won't be in equilibrium. Okay, so what we are going to do in our laboratory, we are creating this force system which is in equilibrium. To keep it in equilibrium, we are changing the magnitude as well as angles or direction of the forces here, so that it should be in equilibrium. And with that force system, we are going to plot the polygon. Okay, and you have to plot the polygon, and you have to prove that in this polygon, if you plot this polygon, the last point will coincide with the first point. If the last point coincides with the first point, you can say that here the resultant is equal to 0. Okay, and hence it is a proof of law of polygon of forces. Okay, because system is in equilibrium, that's why resultant is 0, and since resultant is 0, here the polygon will be a closed polygon. Okay, this is the proof of the law of derivation of law of polygon of forces. Okay. Now after the experimentation, here we have to do the calculation, and in calculation, here we are going to resolve each force into rectangular component. The calculation I will explain you later in the next video. Okay, but we have to resolve each force, and we have to find out the Rx and Ry by using summation of Fx and summation of Fy. And with that of this, you have to find out the resultant. Here, this resultant must be equal to 0. Means graphically as well as analytically, the resultant must be equal to 0. Here, aim of the experiment to verify the law of polygon of forces, and you have to give here only the law of polygon of forces verified. Okay. Now in next video, I will show you the actual experimentation. Here, actual how to take the reading, how we are going to create the force system. And how to prove. Then in the next video, I will explain you how to do the calculation. Okay, remember one thing, this is supposed to be the most lengthy experiment in your engineering mechanics lab. Okay, all together you have to take the 5 readings, you have to draw such type of 5 polygons here. So calculation is also a lengthy part, and performance is also a lengthy part. All other experiments are not that much time consuming. Easily you can do that in 1 hours, but this is little bit time consuming. Okay, thank you. Good morning, student. Today we are going to verify the law of polygon of forces. In my earlier video, I already explained you about the theory of law of polygon of forces. Here, what is law of polygon of forces? How to prove it by using the graphical method. Here, how to add the vectors by using the law of polygon of vectorization. That everything I explained you in my earlier video. Today, we are going to, in our lab, actually verify the law of polygon of forces by conducting the experiment. We are conducting this experiment on this universal force table. This apparatus is known as a universal force table. Now, why this table is known as a universal force table? The reason is that by using this apparatus, we can verify the different laws which we use in mechanics. By using this universal force table, we can verify the triangle law, we can verify the Polygon law of forces, as well as we can verify the Lami's theorem also. Yeah. So, since we can conduct a number of experiments on this apparatus, that's why it is known as a universal force table. On this universal force table, on this disc, the angles are engraved. Here this is divided into 360 degree. You can observe that here these are the marking of 360 degree. Okay, and on this disc here these pulleys are mounted. Because with the help of this pulley we can apply the force on this disc by using these pulleys and the thread arrangement. Okay, this pulley will not provide any mechanical advantage. The pulley is just used to apply the force in a convenient direction. Okay, now this force table is in the horizontal level, so it is very difficult to apply the force in horizontal position. That's why by using this pulley we are applying the force, and it is actually applying on this ring horizontal. Okay, that's why we are using this pulley. Now the position of this pulley, we can lose this screw here and we can change the position, means angle of this force. And we can tie that at particular position. So this is the universal force table. Now other apparatus which we require are the pulleys, then weights, thread and this ring which we have to settle at the center. The different weights which we are going to use here is 100 gram, here 50 gram, 25 gram and 10 grams. All these weights are in the 10 in grams here, and you have to do the calculation. While doing the calculations, you have to convert this gram into the Newton. Okay. Now, for starting the experiment, here the first precautions which you have to take is that this universal force table should be exactly in the horizontal position. Now to check whether it is in the exactly horizontal position or not, here we are going to use here this spirit level. Okay, here and we check whether it is exactly in horizontal position or not. Here you can observe that here that bubble is exactly at the center. Here now also it is exactly at the center, and in this position also it is exactly at the center. Okay, so it is now completely in the horizontal position. If it is not, then by adjusting this leveling screw at the bottom of this universal force table, here you can adjust the force table. Okay, again one adjustment is here also. By unscrewing this knob, here we can change the position of this universal force table also. So by using this leveling screw and this screw, here you can adjust it exactly in the horizontal level. So before starting the experiment, you have to take precaution that here the table should be exactly in horizontal position. Okay, now we are going to start our experiment. Now in experiment, I already told you that in law of Polygon of forces, here we are applying, we are creating one force system in which there will be the 5 different forces. Here we are creating a force system which consists of the 5 concurrent forces. Okay, and while creating this force system, that force system will be in equilibrium. Means the resultant of that force system will be 0. Now law of Polygon of forces states that the number of forces acting on a body are represented by the sides of a polygon taken in order. Then the closing side represents their resultant. Here for that you can refer my earlier video. But now when the system is in equilibrium, here its resultant must be equal to 0. And if the resultant is 0, here that closing side of a polygon which represents the resultant here should be 0 or it will not be there. Means the last point of the polygon must coincide with the first point, then only we can say that the system is in equilibrium, and that only you have to prove. Here with that 5 forces which are in equilibrium, if you plot the polygon by representing the forces graphically, it must be a closed figure. Okay, if it is not closed, then there must be some error in the experiment. Okay, so this is the basic theory behind this experiment. Now next, how to create the force system. Okay, so I already told that with the help of this pulley we are going to apply the different forces at the different angles. Here, the first pulley here, so I'll show it here. This is a ring on which we are applying the 5 component forces. Here, the first force we are always applying at an angle of 0 degree. Here, so this is the 0 degree. We are applying the first force F1. Here, second force we will apply F2 at an angle of this here with respect to the 0 degree we are going to measure the angle. So here theta 1 equal to 0. This is the angle whereby this F1 force with respect to this reference. The reference we are considering as 0 degree. This angle will be theta 2. Here this is the angle whereby this F2 with respect to this 0 degree. Here then this is the force F3. Here and this angle will be the theta 3. Yeah, and this force is F4. The angle whereby this F4 force with respect to the positive x-axis here is making this theta 4, and yet this is the F5, and angle whereby this F5 with the positive x-axis in anti-clockwise direction is theta 5. We are going to measure all the angles in anti-clockwise direction with respect to the positive x-axis. Okay, so we have to create this force system here which will be in equilibrium. So to creating this system in equilibrium, you have to adjust the magnitude of these forces as well as direction so that this ring should be exactly at the center. Okay, here you will observe that here in this force table, here there is one pivot at the center. Here now the ring is touching to the center. Okay, it is not exactly at the center, it is touching to the center. Pivot. And because of that, reactive force is generated. Here, you have to adjust the forces and angles such that this ring should be exactly at the center. Then we can say that it is in equilibrium under the action of these 5 forces. Okay. Now, I am applying the forces here by using this thread and the pulley. And I am creating this force system which keep the ring in equilibrium. Here, so let's apply the forces. Now, at the end of this thread, here there is one hook. And at the end of the hook, here this weight is applied. So this weight is 50 gram. This is the total 50 gram including the weight of this hook. This is total 50 gram. Here this plus weight of the hook, it is total 50 gram. And now we are applying the forces on this. Okay, we are applying the weight. This is 50 gram, here I am applying. Okay, here I am applying the 50 gram, means we become 100. Okay, I am applying here 25 gram. Here also I am applying the 25 gram. Again 50 gram. Sorry, it is 25 gram. Okay, in this way we have to change total altogether. We have to take the 5 different readings. Here by changing the angles and forces. Here for 5 different forces, you can make any combination of the 5 forces and 5 angles to keep this ring exactly in the middle position in equilibrium. Okay, here you can change the forces and you can change the angles. It is little bit time consuming process. Here you have to do a lot of adjustment. Here, now while taking the reading, here take care that this forces, this weight or this angle should not oscillate. Here, so switch off the fans. Here, so it should not oscillate. Second thing, there should not be any friction between the pulley and the belt. If there is a friction, then the applied force and the force acting on the ring will be different because of the friction in the belt and the pulley, or the rope and the pulley. Okay, so there should be a minimum friction. Here, then while attaching the pulley, you have to attach the pulley properly so that here there should not be any. The pulley should not be in inclined position. Okay, you have to attach the pulley properly. Yes, so now it is very time consuming process to adjust the load as well as the angles. Here, so you can adjust the load as well as angles. Here, now here suppose on this side the force is more, this side the force is less. That's why the pulley is moving on this side. Means I require the more force on this side. So I will apply the forces there. Okay, I'll apply the forces here. Now I adjust the forces and angles and then I will show you again. Yes, sir, pause the video. Now you can observe that we have adjusted the weight here such that the ring is exactly at the center. Here it is not touching to this pivot. Okay. Now let's consider this force is a F1 which is at 0 degree. You can observe that it is at a 0 degree. Okay. Yes, so let's consider this as the force F1 which is at the 0 degree and just count how much is the force here applied. Here, so 1 is a 50 and then 25 plus 25 means F1 force is of 100 gram. Okay, yeah, this F1 force is of 100 gram. At an angle of, so this is F1, F2, F3, F4 and F5 for the first reading. F1 is 100 gram which you have to convert in Newton later on. I will explain you how to do the calculation. Here, so this is F1 and theta 1. So theta 1 is 0 degree. Now second force F2. So this is the F2. Here this F2 is at an angle of 79 degree. Theta 2 is 79 degree. And how much is the weight applied here? Here, so it is 50, 25, 25, 25, 25 is 150 and this is 10 gram. This small weight is of 10 gram. Here, so it is 150 and 10, 160 gram. So F2 force is of 160 gram. Here we have applied at an angle of 79 degree with positive x-axis. This you have to consider as a positive axis. Here, then this is the third force. The third force is applied at an angle of here 155 degree. Here take the reading properly, avoid the parallax error. Here, so it is 155 gram. Sorry, 155 angle. Theta 3 is 155. And how much is the F3? The force F3 is, it is 1, 2, 3, 4 and this is 50. Means it is 150 gram. F3 is 150 gram. Now this is F4 force. Here F4 force is 100 and 125 gram. F4 is 125 gram and theta 4. How much is the theta 4? This angle is approximately 240. Okay, it is 240. And this is F5. Here this is again 125 and theta 5. How much is angle? Its angle is 296 degree. Okay, so we have created such type of one concurrent force system here which is in equilibrium. This is 100, this is 160, this is 150, 125 and this is again 125. Okay, yeah, and now with the help of this force system we have to prove the law of polygon forces. Yeah. Now with these 5 forces, if I plot the force polygon by representing these forces graphically, it must be a closed figure because the system is in equilibrium. Since the system is in equilibrium, the resultant force should be 0 and the force polygon must be a closed figure. Here in my next video, I am going to explain you how to do the calculation. Okay, here we can have same reading or I can take a different reading and by using a different reading, I can explain you how we can do the calculation. Okay, here, any doubt? Now if the resultant is not 0, if I plot the force polygon and if you observe that the resultant is not 0, similarly if you calculate the resultant analytically also, here by plotting the force polygon, that is the graphical method. Even if you find out the resultant of these 5 forces analytically by resolving the forces, here the resultant must be 0. Here graphically the force polygon must be a closed figure. Here analytically the resultant must be a 0. If it is not, here the polygon is not a closed figure. If the resultant is not 0, doesn't mean that here the law of polygon is not verified. here that may be because of some error present in this equipment here, because the pulleys may not be exactly frictionless here. Then the forces which we are applying, here we are applying the forces only 10 gram, 25 gram and 50 gram. Here for exact equilibrium, here the force may require 165 gram, 175 gram, and it is little bit difficult to prepare that combination in our lab. Okay, yeah, so because of some error, experimental error, here we are not getting the exact result, but yeah, even if you are getting some resultant, but the resultant will be very small as compared to these applied forces. Here, if that applied forces are 100, 125, 160 gram, so even if some experimental errors are there, so graphically or analytically, if you calculate the resultant, it will be very less. Here maybe 1 gram to 5 gram. Here, this is because of this experimental error. Yeah, thank you. In the next video, I am going to explain you how to do the calculation with this. Yeah, so you have to do the calculation and you have to write down the conclusion and result. Okay, thank you. Good morning, students. In our second lecture video, I explain you how to perform the experiment to verify the law of polygonal forces. Yeah, the first video was about the theory of law of polygonal forces. Second video was about the performance of the experiment. And now this is the third, in which I am going to explain you how to do the calculations. Okay, and I am going to show you the sample calculation and similar kind of calculations you have to do, and from your calculation you have to write down the conclusion and result. Okay. Now I already told you that in this experiment we have to create a concurrent force system which consists of the 5 forces, and that force system should be in equilibrium. So we have taken some readings here, and this is the sample calculations here for a particular reading of a particular force system which is in equilibrium. So theta 1 is the inclination of the first force F1 with respect to the reference line on that force table. Yeah. So first force is inclined angle of 0 degree. Second force of 200 gram. These are the forces in grams. Yeah. So 200 gram inclined angle of 74 degree. Third force is 175 grams, inclined angle of 150 degree. Fourth force 150 grams, inclined angle of 280 degree. Fifth force is 175 grams, inclined angle of 291 degree with respect to the positive x-axis in anti-clockwise direction. Okay. Now these forces are converted into Newton also. Yeah. Now how to convert the forces into Newton? Yeah, we know that 1 kg equal to 9.81 Newton. Yeah. So convert this gram, 150 gram divided by 1000 into 9.81 gives you the force in Newton. So in this way we can convert it into Newton. Okay. Or even if you keep it in the grams, doesn't make any difference, because anyhow we have to verify the law of polygonal forces. Doesn't make any difference whether it is in the gram or the Newton. Okay. Now to verify the law of polygonal forces graphically, we have to construct the space diagram as well as the force diagram. Okay. Now in space diagram, the first one is a space diagram. Now what is this space diagram? In the space diagram we are going to show this force system here with their angles. Here in this space diagram we are supposed to take the scale to represent the space, to represent the distances. But since our system is a concurrent force system, we no need to take the scale to construct the space diagram. If it would have been a general force system, then we have to take the scale to represent the distances in the space diagram also. So with this readings what we have taken here for this force system, we are going to construct the space diagram. So let's consider this is our one reference line here on x-axis or 0 degree, and here that ring is here. Here we are going to show all the forces acting on this ring. Okay, this is the y. Here. So our first force, here 150 gram, here F1 is acting along the positive x-axis because theta 1 is 0, so this is the force F1. Then with the help of protractor, you can take this angle 74 degree with positive x-axis in anti-clockwise direction, and you can show the force F2. This is F2, this angle is theta 2. which is equal to 74 degree. The third angle is 150 degree where the force F3 is acting. Yeah, so this is the third force and this angle is theta. Okay, 115. Approximately I have shown, but you have to use the protractor and you have to take exact angles and then you have to show this force F3. Okay, no need to bother about the length of these vectors. Okay, in space diagram, we have no need to bother about the magnitude of the force. Okay, means the length of that particular vector. Then next force F4, 150 gram, inclined angle of 210, 18. Yeah, so this is 90, 180. So approximately here, this is F4, 150 gram, inclined at angle of theta 4. So this angle is theta 4 with respect to positive x-axis. Here all angles with respect to positive x-axis in anti-clockwise direction. Yeah, and the fifth force is 175 gram, inclined angle of 291 degree. So this is fifth force. Here inclined at angle of 291 degree. So this angle is theta 5, which is 291 degree. So this figure is known as a space diagram in which you have to show all the forces with their actual angles. Okay, but technically in space diagram we are supposed to, once we have shown these forces, we are supposed to give some names to the space between the forces here, and that is known as a Gauss notation. In oral examiner may ask you about this Gauss notation. Actually this part is not included in your theory syllabus, but in practical you can tell about this Gauss notation. Now what is the Gauss notation? Here in this graphic statics, here when we solve the sum by using the graphical method, in that graphic statics, here when we construct the space diagram, in this space diagram the space between the forces is represented either by some numbers or the letters. Okay, and that is known as the Gauss notation. Here for example, suppose the space between F5 and F1 I am going to denote it by capital A. Similarly, this space I am going to denote by B. This is C, this is D, this is F. Okay. So these are known as a Gauss notation, and once you have denoted the space with the help of these capital letters here, this force F1 is denoted by the force AB. Here, this force, line of action of this force divide this space into two parts A and B. So this force is denoted by the force AB. This force is denoted by force BC. This force is denoted by force CD. In this way, we have to denote the forces after giving the Gauss notation. Here we are going to do this Gauss notation in the force diagram. Yeah. So I hope here is it clear how to draw this space diagram. Okay. Now next one is the force diagram. To construct this force diagram, this space diagram is necessary. Here, so this is the force diagram. Don't draw the space diagram directly. Here you have to take actual angles and you have to construct this space diagram. Now in force diagram, you have to represent these forces graphically. And to represent the forces graphically, we have to select some scale to represent its magnitude. Yeah. In the first video, I explain you how to represent the force graphically. Here you can refer that video. Okay. So in force diagram, we are supposed to represent this magnitude of the forces graphically, and for that we have to take the scale. Okay. Now you can take the scale in Newton, you can take the scale in grams. Here, but it is easy if you take the scale in grams. Here, so I will suggest better you take the scale in grams. Here, because all these values of the forces are in grams and these are the number here where it is in the decimal point. Okay, so better you take the scale. Now to take the scale, you have to remember that the force diagram should not be very small or should not be very large so that it should not fit on your page. Here, for that just observe what is the minimum force. So minimum force is 150, maximum force is 200. Yes, so according to that I will take the scale. So for this I will select the scale. 1 centimeter is equal to here 25 grams. 1 centimeter equal to 25 grams, or 1 centimeter equal to 25 upon 1000 into 9.81 Newton. Same scale I have converted into Newton. Okay, or you can take 1 centimeter equal to approximately 4 Newton. Okay, or 1 centimeter equal to 2 Newton. That also you can take. Okay, you can change the scale. Yeah, and accordingly you have to represent the magnitude of the forces. So I will select the scale 1 centimeter equal to 25 gram. Then to write down the final answer I am going to write it in Newton only. Yeah, and then for writing the final answer I will convert it into Newton. But for drawing the force diagram I will take it in the grams only. Okay. So what you have to do in the force diagram, you have to represent this magnitude of the forces graphically, or you have to represent these forces graphically. Yeah. How to represent this force F1 graphically? I told you that to represent the force F1 graphically, draw the line parallel to the line of action of this force F1. Now this force F1, how much is this? It is 150 gram. Now to represent this 150 gram according to this scale, how much length I required? So 150 divided by 25, so I require the 6 centimeter. Okay, yeah. So from this take one A point, and from this point draw the line parallel to the line of action of this F1. Or this F1 is inclined at an angle of 0 degree. Here, so consider this as a 0 degree. Here, draw a horizontal line here to represent the force of 150 gram. To represent the force of 150 gram, according to this scale, we require a length of 6 centimeter. But don't write here 6 centimeter. Actually, this 6 centimeter length represents the force of 150 gram. Okay, yeah. So you have to represent this force F1 150 gram, yeah, by drawing a line of 6 centimeter. Yeah, so this is F1 which is equal to 150 gram. And this force is represented by AB, by the Gauss notation. Okay. Then law of polygon states that the number of forces are acting on the body are represented by the sides of a polygon taken in order. The closing side represents their resultant. So we have to represent all these forces in sequence here in order. Means the next force you have to start from this heading. Yeah. Now I am representing this force F2. To represent this force F2, draw the line parallel to the line of action of this force F2. Yeah, either you take the line parallel to the line of action of this force F2 because we have constructed this phase diagram by taking the actual angles. If not possible, then this F2 is inclined angle of 74 degree. So draw the faint line here and adjust the protractor here and draw the line inclined at an angle of 74 degree. Okay. Now this F2 is 200 grams, and to represent this 200 grams according to this scale, here we require the length of 8 centimeter. So this BC line represents a force F2 here which is equal to 200 grams. According to this scale, here this length will be 8 centimeter. Okay. Then we have to represent this force F3 as a third side of a polygon. This inclined angle of 150 degree with positive x-axis. So here you draw one horizontal line parallel to this line. Here and adjust the protractor here and draw one line inclined at an angle of 115 degree with positive x-axis. So this angle is 150. Here and the CD line represents the force F3. Okay, even if both the figures are on the same page, you can draw the line parallel to this. Here you get at 150 automatically. Here if not possible, adjust the protractor here and construct this 150. Yeah. Then from this head end, you have to construct the next force. Next force is the F4. Here which is inclined at an angle of, at what angle F4 is inclined? 280. So draw the horizontal reference line here and adjust the protractor here and with this take to this positive x-axis, draw a line inclined at an angle of 280 degree. F4 is 280. Okay. Now F4 force is 150 grams here. So draw the line DE. This D, sorry, actually it should be E, not F. So DE force represent this DE line represent the force F4 whose magnitude is 150. To represent the force of 150 gram, here we have to, according to this scale, we have required the 6 centimeter length. Okay, here and then from this represent this force F5, draw the line parallel to this F5. Okay, so this EA, don't write it as a EA, write it as a A dash. If it coincides with A, then also you write it as a A dash. Okay, so this EA line represent the force F5. Here this F5 force 175 according to this scale we require a length of 7 centimeter. Okay, it inclined angle of 290 degrees. So with respect to this, draw one horizontal line here, adjust the protractor here, and with respect to this positive x-axis, draw a line inclined angle of 291 degrees. Okay. Now, after representing this force F5, if you observe, here this system is in equilibrium. If this system is in equilibrium with these 5 forces, if you plot the force polygon, it must be a closed figure. Here this last point must coincide with the first point. If this last point coincides with the first point, means your law of polygon of forces verified. Here, because it is in equilibrium, and if it is in the equilibrium, the polygon must be a closed figure. Okay, so if it coincides with the last point, here it is more accurate. Yeah, but if it does not coincide with this point, yeah, then this closing line represents their resultant taken in opposite order. So this A dash represents the resultant of this force system. Here it is very small. Even if you get this, it will be very small. Yeah. Then this A dash line represents the resultant. So measure this line here. So this resultant R is equal to measure this length A dash and multiply it by the scale. Okay, suppose this A dash length, if you get it as 1 centimeter or if you get it as a 0.5 centimeter, measure this A dash. If it is 0.5 centimeter multiplied by 25 grams, so which is equal to 12.5 grams, means the resultant is 12.5 grams, and now you can convert it into gram. 2.5 divided by 1000 becomes kg into 9.81, so it becomes Newton. Okay. Even if you get this resultant, you will find it very small, very small, and this because of the error in the experiment. Okay, yeah. Now, this is the inclination, sorry, this is the magnitude of the resultant. Now, find out its inclination also. Let it is alpha. If it is not possible to measure this alpha over here, extend this line of action and somewhere you measure the alpha and write it here. This is the alpha. Here, this is the graphical resultant, and this is the its inclination or its direction, okay, with respect to the positive x-axis here. So this is the graphical method. Here you will get this resultant, small resultant, and its inclination, and in conclusion you are supposed to write this here, how much resultant we got here, and if it is very small within some limit here, you can say that here the law of polygon of forces verified here. Okay, in conclusion we are supposed to write why we got the resultant. Even if the system is in equilibrium, okay, the resultant should be 0, but we got a very small resultant. In conclusion, here you have to write down that, or in inference you have to write down that. Here, why we got that resultant. Okay, this is because of some experimental error. Here the pulleys are not exactly frictionless. Second one is there may be some parallax error. The third one, maybe we are taking the readings in 25 grams, we are not applying the force less than 25 grams here, and because of that also there may be some error. Now again, one part of actually here itself is a law of polygon of forces and it is verified here, but apart from this, here from this base diagram here we have calculated this resultant graphically. Now let's calculate the resultant analytically also, and just cross check whether the analytical resultant and this graphical resultant both are correct or not. This is just a verification. Analytically and graphically we are getting the correct answer or not, or same answer or not. Okay. Then what is the procedure for finding the resultant of the constant force system analytically? This was the graphical. And to find out the resultant analytically, we are going to use the method of resolution. We are going to use the method of resolution. Okay. In which what we are going to do? We are going to resolve each force into two rectangular components, and we are taking the summation of all x component by using the proper sign convention, summation of all y component by taking the sign convention by using some sign convention. Here and we are going to calculate the x component and y component of resultant. Okay, here for this also you can refer the first video. Here, so each force you have to resolve into two rectangular components along x and y axis here, and you have to find out summation of fx. Here, this is the summation of all x component by taking proper sign convention. Here, if the component is acting towards right, you have to take it positive. If the component is acting towards left, you have to take it negative. So this x component of this F2 is towards right, it will be positive. The y component of this force F2 will be upward, so it is positive. Towards right, positive, upward positive. Towards left, negative, downward, negative. Okay, so this is F3x and this is F31. Here, in this way, you have to resolve each force into two rectangular components, and you have to take the summation. This is F1 plus F2x minus F3x. Here minus F4x. That way, you have to take the summation of all x components. But now here, when we resolve it in this way, here if this angle is suppose alpha, or let this angle is suppose beta, then this F3x will become F3 cos beta. This beta is the acute angle made by this line of action of this force F3 with horizontal. But instead of writing this angle beta, because we know this theta 3, listen carefully. Suppose this is F3, this angle is theta 3, and if this angle is beta, here then this component will be F3 cos beta. Okay. Now if you want to write down it and it is acting towards left, so this will be minus F3 cos beta. But if you want to write it in terms of theta 3, then you can directly write down plus F3 cos of theta 3. Because this theta 3 is greater than 90, it will be 90 plus some angle here, and cos of 90 plus something, here this value will automatically get negative. Okay, so you don't have to bother about that. Okay, yeah, same thing about the sine component. So this summation of all x component can be written as f1 cos theta 1 plus f2 cos theta 2 plus f3 cos theta 3. You may say that this is towards left, why you are taking positive. So remember this theta 3 which is greater than 90 degrees, that angle itself will take care of this sign. Okay, here plus f4 cos theta 4 plus f5 cos theta 5. Here just you have to substitute the value and get the answer. Here we will get the summation of fx. Here the summation of fx represent the x component of resultant. Okay. Similarly, here calculate the summation of all y component of the forces. Here and in y direction it will be the sine component, so it is f1 sine theta 1 plus f2 sine theta 2 plus f3 sine theta 4. Sorry, sine theta 3 plus f4 sine theta 4 plus f5 sine theta 5. Now here also, here for y component of this f4, vertical component of this f4 is vertically downward. So actually it should be negative. But remember that angle will itself will take care whether it is positive or negative. You don't have to bother, always take it positive. Because we are taking the angle made by all the forces with respect to the positive x-axis in anti-clockwise direction. Here just everything is known to you, substitute the value, take all the thetas in degree here and calculate the summation of fy which represent the ry. So we will get the summation of fx and summation of fy. Here means we have converted this 5 force system into this 2 component system or 2 force system. Here by using summation of fx and y, summation of fx and summation of fy, we have converted this 5 force system into 2 force system. Here this is summation of fx or rx and this is summation of fy which is equal to ry. And we are converting these 2 force system into a single force system which is the resultant. Yeah, so that resultant is given by r equal to under root of summation of fx square plus summation of fy square, because these are the 2 rectangular components of that resultant. Just substitute the value and get the answer, and then this inclination of this resultant with horizontal alpha can be written as tan inverse of mod of summation of fy upon summation of fx. This is the angle made by the line of action of the resultant with horizontal. Here and this answer should match. Okay, here error तो है ही, there is a error, some small error you will get. Yeah, but just cross check whether you are getting the same error by analytical as well as by graphical method also or not. Yeah, so this resultant and this resultant should match, this alpha and that alpha should match. Okay, yeah, so for each observation, yeah, you have to draw the space diagram, force diagram and sample calculation or analytically you have to do. Yeah, this everything you have to do for one calculation, and that this way you have to take all together 5 readings. Here, this in first experiments all together you have to draw the 5 space diagram, 5 force diagram and 5 graphical methods. Here, and in result table you have to tabulate all these things. Here we provide you here the write up. Here in the write up result table also here you have to write it in that write up, and for each experiment you have to do all these calculations. This space diagram and force diagram, if you want, you can draw it on the graph paper also. Okay, here it is not that useful here, but if you want, you can draw graph paper also, or on the plain paper also. If you draw, it's okay. Okay, in journal which will provide here in that journal, there will be a graph paper. Yeah, so you can plot it on the graph paper. Yeah, and these are the space provided for the calculation. So this analytical calculation you can do it here, and at the end you have to write down the result table, conclusion. Here, and these are some discussion, some points are given. Here you have to write down the answers in your own word. Okay, that will use the inference. Okay, that answer itself uses the inference. Yeah, so this is all about the first experiment. Here in conclusion, you are supposed to write down how you have verified the law of polygon of forces in your word. Here you have to write down the conclusion properly. Yeah. Any doubt? If you have any doubt, you can ask your teacher. Yeah. Those who are conducting the practice. Yeah. Thank you.